Let's go ahead and get through these three problems. I have the point 2 comma 4, and there's some sort of transformation that changes it to 1 comma 1. I'm asked to use that same transformation on this one here, and then it'll turn it into what? And then it tells us, and that word's really important, translation. That means we're adding or subtracting some number to the original. That's the translation that gives us that output. So we need to find out what that translation is. So I'll call it, let's see, what letter? I'll call it S. So 2 plus the translation S gives us 1. And this is the X component. So I'll call that, I'll call it like as a part of the X. So this portion we need to now solve. So that's -2 to both sides. What you do to one side, you do to the other. So I'm using reverse operations to get S by itself. The S drops straight down. The equal sign drops straight down. 1 minus 2 is -1. So the translation on S, on the original X is -1. Now we need to go ahead and do that for the Y component. So what translation is going on Y here? So we start off with our original 4, and it gets turned into an A, B, C, D, I'll use E. No, that's not a good one. F, G, H, I, J. Let's use J. 4 plus some J that changes it is equal to, and it changes it into that one right there. So we'll go ahead and use our reverse operations again to get J by itself. So that's a -4, that's a -4, and I get J is equal to, I like dropping the equal sign straight down, -3. So the change on this one and this one is a -1 and a -3 respectively. So this now turns into -3 minus 1 on the X part, comma, and on the Y part, it is the 0, and that's a -3 that gets applied to it. This all turns into the final answer. So -3 comma 0, when it has that translation applied to it, turns into -4, comma, -3. Next one. We are reflecting 6 comma 2 over the origin. Okay? So for these, it's a lot easier to do them graphically so we can kind of see what's going on. It'll be a lot easier to count how it kind of changes with respect to that. So let's plot it. 1, 2, 3, 4, 5, 6. 1, 2. And it looks like we're going to wind up in quadrant 3 here. So this is my 6. This is my 2. Here's my point. And then we are reflecting it over that point there. So what that means is we need to see the kind of the rise and run, so to speak, the change in the X and the change in the Y to get there, and then we apply it to the same way on the other side. So this is 1, 2, 3, 4, 5, 6. So that's a distance of 6 right there. This distance right here, 1, 2, is a distance of 2. So the change in Y, that's a delta Y, is 2. The change in the X, that's an X, that's a Y. The change in the X was 6. So we apply that same change on the other side right here. So the change on this side is going to be a change in Y of 2, 1, 2. So now we're at -2 on this one. So the delta Y is equal to a change of 2 in this case. And I'm not worried about the plus or minus, we're just looking at how it changes. And then we're going to go 1, 2, 3, 4, 5, 6 on that side. At -6. So notice it has that same distance from the origin. And that's kind of key. It's like when you look at yourself in a mirror, you are to the mirror is the same distance as your reflection is to the mirror. So what's this point? -6, -2. Reflect 6, 2 over the origin. Yes. And one of the things that the presenter in Delta Math kind of talked about, a reflection over the origin is the same thing as a rotation of 180 degrees around the origin. And a rotation of 180 degrees around the origin, it just negates or does an opposite on each of the components. So 6, 2 turns into -6, -2, and that's always going to be the case if you're reflected over the origin. Last one, -3, -3 has a dilation scale factor of 1/3 at the origin. Once again, let's go ahead and draw the graph to make it a little bit easier to kind of see and compare, and we do a lot of the similar techniques that we did in this last one. So let's x and y, 1 to -3 on the x, and 1 to -3 on the y. So there's my point there. Now a scale dilation makes something either bigger or it makes something smaller. So in this case, a scale factor of 1/3, do you think that's going to make it bigger or smaller? Well, a scale factor, a factor is kind of like a multiply. If you multiply something by 1/3, you're making it smaller by 1/3. So from the origin, it's going to get closer to the origin if we do it correctly. But once again, we need to see how far it is, how far are the x's away, how far are the y's away, and then we'll apply that scale factor to those. So I'm looking at compared to that one, and it doesn't matter if you go up, down first, or left, right first. I'll go ahead and just do the up first. So that's 1, 2, 3. So there's a 3. And then we'll go to the right to get to that point. And that's a 3 also. So the trick is we take this scale factor and we multiply it by these numbers. And then that's going to be where the new point is going to be at. So 3 times 1/3. Okay. Well, a couple different ways of doing it. A number times a fraction always multiplies to the top. You can also think of it, so that trick, a number times a fraction multiplies to the top, that would be 3/3. And I'm running out of space here. 3/3, that would equal 1. Another way of doing it, 3 times 1/3, is make that, you can always put a 1 on the denominator, and we multiply straight across. That turns into 3/3 again, which is equal to 1. Or you could cancel. So this 3's on top, this 3's on bottom. It's like there's 3's on top, 3's on bottom. They reduce, and all we're left with is 1. So notice it's the same for both of these. So that means the new adjustment is going to be 1. So this 3 turns into a 1. That 3 turns into a 1. So from the origin, it goes 1 on the x, 1 on the y in that same direction, and there is our new point that's been dilated. And it should make sense because it's kind of like a distance idea, is that this point is 1/3 the distance as that point.